Hello students, in this video we will continue with the topic of solid state. In solid state what we were studying is about the different types of defects, where we have studied stoichiometric defects, impurity defects, non-stoichiometric defects. Stoichiometric defects, we have studied Schottky defect, Frenkel defect, examples for it. Then we have studied impurity defect. In impurity defect, we know due to presence of impurity atoms there, the defect is caused. And here again, coming back to stoichiometric defect, what I mean to say is stoichiometric defect is the one in which stoichiometry is not affected. Now we are studying about one more type of defect called as non-stoichiometric defect. Non-stoichiometric defect, and non-stoichiometric defect are those defects which affects the stoichiometry of the solid, that is crystalline solids. Stoichiometry will be affected or will be disturbed. So in general you can say non-stoichiometric defects are those which disturbs, or the defect which disturbs the stoichiometry of solids. I'm just reminding you these points. In this again we have studied that we have two types, where we say metal excess defect, metal deficiency defect. Metal excess defects are those in which the positively charged ions will be more in number compared to the negatively charged ions. Am I right? In that we have studied one example where in metal excess defect we consider an example of sodium chloride crystal, in which when the sodium chloride crystal is heated in the presence of sodium vapor, what happens? The sodium ions come and get accumulated on the surface. Now some negatively charged species move there and react there. Now there is an anionic vacancy. Anionic vacancy means the negatively charged species which has gone out, that space is vacant. That space will be filled by an unpaired electron. From where did you get that unpaired electron? Sodium gets converted into Na+. If it has to convert into Na+, Na gets converted into Na plus by losing one electron, right? That is why it has got 1 plus charge. So if it has to get 1 plus charge, one electron goes out. That one electron which has gone out, now we call it as unpaired electron. It doesn't have a pair, it's a free electron. The unpaired electron comes and occupies the anionic vacancy. Anionic vacancy means the vacancy created by anion. So what is F center? F center is the center where the anionic vacancy is filled by an unpaired electron, or unpaired electron occupies anionic vacancies, which imparts color to the crystal. It's also called F center or Farben center or color center. What is the role of this? It imparts color to the solid. Hope it is clear. Now we will see, we have studied one more where in metal excess defect we took an example of zinc oxide. When the zinc oxide is heated, what happens? It loses oxygen. Zinc oxide loses oxygen. So Zn gets converted into Zn2 plus by losing 2 electron. Yes. Now what happened? Oxygen got escaped, but now zinc is more now. That is why we also write it as Zn. It was 1 earlier, now 1 plus X. That means some X amount of ions are more there. So Zn will be more compared to O. So than the normal stoichiometric ratio expected, now the stoichiometric ratio will be different, which means that it is non-stoichiometric defect. So this is an example for metal excess defect. Now it is clear why it is called as metal excess defect, because here metal is present in excess. Now what we are going to study is one more defect called as metal deficiency defect. Metal deficiency defect. Metal deficiency. Deficiency means where the metal is less in number compared to the negatively charged species. Hope it's clear. Now, positively charged species, if we say metals, so it will have positive as well as negative charges, isn't it? Now here, say the metal deficiency means the positively charged species, so the metal ions will be less in number compared to the electrons. So that is what we call as metal deficiency defect. Now in metal deficiency defect, let us see, there will be some metals which is difficult to prepare it in the expected stoichiometric proportion. So we may not be able to prepare a compound or a solid which is expected as per the stoichiometric ratio. One example is FeO. What is FeO? Iron oxide. Now this iron oxide, what is the expected stoichiometric ratio? Expected stoichiometric ratio is F is 1, that is iron is 1, oxygen is 1. But in fact what happens is, we expect the stoichiometric ratio to be 1:1, but it doesn't happen so. Instead, this iron and oxygen will be present in the ratio. Iron will be present as 0.95, whereas oxygen will be present as 1. So you can make the difference. It's not exactly 1, it is 0.95. That means there is deficiency of the metal ions. Fe is the metal ion, Fe2 plus O2 minus. Here Fe2 plus O2 minus. So positive and negative charge gets balanced, and that is why you don't mention anything here. But as per the stoichiometric ratio, it doesn't take place. Instead, there will be deficiency of the metal ions, and such a defect is called as metal deficiency defect. So how will you write? In some cases, it is not possible to prepare a solid of expected stoichiometric proportion. Expected stoichiometric proportion. That means preparing a solid of expected stoichiometric proportion is not possible. And this leads to a defect where the metal ions will be less. This leads to a defect called as metal deficiency defect. Example, FeO, where it should have been 1:1 ratio, but the ratio will be 0.95:1. And usually the expected range is Fe can range from 0.93 to 0.96 also. This is the expected range of its composition or proportion of that particular metal ion. Now, this was about the stoichiometric, that is non-stoichiometric defects that we were studying. Now, next we will be studying about an important concept related to the solids now. And here do remember that whatever there is deficiency, isn't it? Deficiency means less number of metal ions. Fe2 plus is less, so that will be compensated by using Fe3 plus ions in the place of Fe2 plus. No, because it is less, it will be compensated by Fe3 plus ions also. This is for your knowledge. Now let us study next property of solid, that is electrical properties of solids. Electrical properties of solids. Electrical properties of solids means how actually these solids shows conductivities. Conductivity means we know conduction. For example, we say solids or metals are good conductors of electricity. Metals are good conductors of heat. How do we say that? It is when they can allow the heat to pass through it or the electric current to pass through it. Am I right? Now here we will be seeing the electrical properties of solids. Mainly we will be considering three important terms here. One is called as conductors, insulators and semiconductors. So these you'll be aware of these terms. However, electrical properties of solids means here the solids have an ability to show the electrical conductivity ranges. There is electrical conductivity ranges for different types of solids. So the solids can be classified as conductors based on their electrical conductivity range. Based on electrical conductivity range, solids are classified as conductors, insulators and semiconductors. Now here, if suppose the metals show a conductivity range, electrical conductivity range between 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse. This ohm inverse meter inverse is the unit for electrical conductivity. If the electrical conductivity range is 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse, then we call such substances as conductors. Conductors means they can conduct electricity. They can allow the electric current to pass through it, electrons to pass through it. That is what it means. So what are conductors? The substances in which the electrical conductivity range lies from 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse. We call such substances as conductors. Then what are insulators? In insulators, the conductivity range will be 10 to the power minus 20 to 10 to the power minus 10 ohm inverse meter inverse. So you can just imagine how small the conductivity range is. 10 to the power minus 20. 10 to the power minus 20 means it is 0.000 some 19 zeros and then 1. So that small the conductivity range is. 10 to the power minus 10 per ohm per meter, in the sense again you can imagine how small the conductivity range is. So based on the conductivity range we have conductors, insulators, semiconductors. Now let us see what are semiconductors. So semiconductors are those whose conductivity range lies in between that of conductors and insulators, whose conductivity range will lie between conductors and insulators. And again in this the conductivity range will be 10 to the power minus 6 to 10 to the power 4 ohm inverse meter inverse. This is about conductors, insulators and semiconductors. Now we will move on to one more part where we can classify this conductors, insulators and semiconductors, or how we can study this based on valence band theory. Band theory of solids we say. Band theory of solids. Now let us see how we can know about this solids. You know, in the case of metals, if we say, or in case of any solid substances, the atomic orbitals will combine. Now you know atomic orbitals where the electrons will be filled. Now atomic orbitals, two or more atomic orbitals combine to form a molecular orbital. Okay, what is it? Atomic orbitals. You will be studying this in chemical bonding chapter. Atomic orbitals, two or more atomic orbitals combine to form molecular orbitals which can be generally called as bands. In general, we can consider them as bands. Now, what is this band? Actually, we say a valence band, a conduction band. Okay, a valence band, a conduction band. Valence band means, say, the empty band. Conduction band means where you have the electrons filled up. So, based on that, we can consider conductors, insulators, and semiconductors also. Now we will see, in case of conductors, what happens. This is based on band theory we are speaking now. What happens we will see. In the case of conductors, so you will have bands. Say for example, this is a band which is called as empty band or valence band, we can say. Empty band, and this is conduction band. Conduction band, or you can also call this as valence band and this as filled band. In case of conductors, what happens is, if this band is partially filled means it is filled with electrons but partially, half filled or partially filled. If the space or if the energy gap between the conduction band and the valence band is very less, if the energy gap, this is called as energy gap, or it's also called as forbidden gap, I'll tell about that. If the energy gap between the conduction band and the valence band is very less, then we call the substance as conductors. Why? Because now here the electrons will be partially filled, isn't it? It's very easy for the electrons to jump from this band to higher energy band. This band, empty valence band, will be having higher energy. So it's easy for the electrons to jump from lower conduction band to higher empty band. Now it's easy for the conduction of electrons. This is one possibility. Otherwise, if the energy gap is small. Otherwise, one more possibility is if there is overlapping of bonds. Overlapping of bonds means if the bond is overlapping on one another. If this is empty band has overlapped with the conduction band. Even now, it's easy for the electrons to jump from lower energy level to higher energy level, and then the conduction of electrons to take place, which leads to the conductivity of the electrons, and that these such substances are called as conductors. So hope you can explain what are conductors. You will tell the conductors are those substances in which that is the energy gap between conduction band and the valence band is very less. Otherwise, one more way, conductors are the substances in which the conduction band and valence band has overlapped with one another, where there is overlapping of conduction and valence band. This is how we will explain for conductors. Now let us see what is it for insulators. In the case of insulators, this energy gap will be very high. In the case of insulators, the energy gap will be very high. I'll just write it here for insulators. If suppose this is the valence band and then this is the conduction band, there will be large difference. The energy gap, or it is also called as forbidden gap. Forbidden gap will be more here. So in the case of insulators, what happens? The energy gap or Forbidden gap, Forbidden, forbidden gap is very large energy gap or forbidden gap between which band? This is called as conduction band, and then here it is called as valence band. So here in the conduction band less number of electrons will be present, and because the energy gap is very large, there you cannot see the conduction of electricity. That is, the electrons cannot easily jump from conduction band to valence band, and therefore it cannot conduct electricity, or it cannot show the conduction of electrons taking place easily. Okay, then one more thing which you have to note. Okay, please make a correction here that this is valence band and this is the conduction band. This is valence and this is conduction band. This helps in conduction. So if the electrons jumps to conduction band, then conduction will be shown. Whereas this is valence band. Valence band is that space where the valence electron will be present. So this will be valence band and this is the conduction band. Okay. Now in the case of conductors, what had happened? The conduction band and valence band had overlapped. Because of the overlapping, the electrons can easily jump from valence to conduction band, and hence the conduction takes place. And one more thing is that there might be a possibility that it can be a partial filled orbitals, valence band orbitals. Otherwise, it can be a completely filled one. If it is completely filled, then it is very easy for the electron to jump from lower energy to higher energy. It means the gap is very small. The electron from lower energy can easily jump to the higher energy. Whereas in case of insulators, what happens? The energy gap will be very large. From lower energy, the electron to jump to higher energy, it requires more energy, which is not possible in the case of insulators. So in such substances, the electrons cannot jump. Now let us see what about it in case of semiconductors. In the case of semiconductors, what actually happens? In semiconductors, what happens is, compared to conductors, the energy gap will be less, but compared to insulators, the energy gap will be a bit large. If this is conduction band, and this is valence band, the energy gap will be slightly larger than that of conductors, but less than that of insulators. That you need to mention. Okay. So what happens from the valence band? If the electrons is partially filled, then to jump to the higher energy level, it needs some support. Support in the sense some external factor is required. So usually what is done is, the semiconductors, electrical conductivity lies in between that of conductors and insulators. So in between, semiconductor comes. In this case, the conductivity can be increased. Example for semiconductors are, now you know the examples for conductors, insulators, isn't it? Conductors example can be any metals like iron, copper. All these can be the example for conductors. Insulators, the other example, some other compounds can be the example which does not conduct electricity. For example, plastics, all those. In case of semiconductors, example, silicon and germanium. Silicon and germanium are the examples, important examples for semiconductors. Germanium is denoted as Ge. Now, how the conduction can be increased? Electrical conductivity of semiconductors can be increased by a process called as doping. What is it? Electrical conductivity of semiconductors can be increased by a process called as doping. D-O-P-I-N-G, doping. Now, what is doping? In the process of doping, what exactly is done is, the semiconductor is taken, it is treated with some electron rich species or electron deficient species, so that, now this is called as pure type of, it is called intrinsic semiconductor. Intrinsic semiconductor means pure form of semiconductor it is. Now what will be done? This intrinsic semiconductor is taken, it is treated with some impurities. It can be electron rich or electron deficient impurities, so that when you treat with such impurities, what happens? It can conduct electricity. It can show more conductivity. Now let us see how. So what is the process of doping? Doping definition. Doping, the process of adding impurities to the intrinsic semiconductor. Intrinsic means, I have told you, pure semiconductor. Intrinsic, I-N-T-R-I-N-S-I-C, intrinsic semiconductor. To increase its conductivity. This process is called as doping. Now let us see how the doping is done. There are two ways of doping. One is using electron rich impurities, other one is electron deficient impurities. We'll see how using electron rich impurities the doping is done. Using, that is doping using electron rich impurities. Using electron rich impurities. Now here what is done? Silicon and germanium, they belong to group 14. Okay, they belong to group 14. This is for your information I'm explaining. Usually how the questions will be asked is to differentiate between N-type and P-type semiconductor will be asked. I will explain you what it is. Now please do understand the concept that silicon and germanium, they belong to group 14 elements. So you know the valence electrons or the valency of silicon and germanium will be 4. That means if valency is 4, that means it can form maximum of 4 bonds. So silicon or germanium, if you consider, it will have 4 electrons which it can share with the neighboring atom. So if there is any other neighboring atom, it can form a bond here. 2, 3, 4. So maximum how many bonds it can form? 4 bonds it can form. Silicon and germanium. Now this silicon and germanium, now this is intrinsic semiconductor. It is doped with electron rich impurities. Electron rich impurities. Electron rich impurities means they must have extra electrons, right? So it is doped with group 15 elements. Group 15 elements like phosphorus or arsenic is taken. phosphorus or arsenic it is doped with. Now what is the valency of this? Valency of group 15 elements will be 5. One extra electron you can see. Here 4 it was, but here 5. So it will have how many electrons? 5 electrons this will have. Which one? Phosphorus and arsenic. Now what happens? See, this is how it looks like. If you consider a solid system or a crystalline solid, then it is like all silicon. If it is silicon, all silicon, isn't it? Silicon, silicon. All silicon atoms will be present in silicon crystal. This is intrinsic semiconductor now. All same type of atoms are present. Now here what happens? You are doping it. Doping it means you are treating it or you are mixing a group 15 element here. A group 15 element when you are mixing, that is phosphorus or arsenic, what happens? It comes and occupies any one side of this silicon. Say this has been occupied by, now you are doping it with phosphorus. Phosphorus has occupied that place. How many electrons does phosphorus have? Phosphorus has 5 electrons, whereas silicon, you know, it had 4 electrons like this, 1, 2, 3, 4, and this used to form a bond with the neighboring one, 4. Then again this forms a bond. All had 4 electrons around it. Same way I'll write for these. Here 1, 2, 3, 4. Same way here 1, 2, 3 and 4. Now what about phosphorus? Phosphorus has 5 electron. So what it does, you know? This silicon has 1 electron. So this phosphorus 1, 2, 3, 4. So with neighboring 4 silicon atoms, it forms a bond here. 1, 2, 3, 4. It forms a bond. What about the 5th electron? Now the 5th electron here is free. Isn't it? Phosphorus has 5th electron which is free now. What does that 5th electron does? Or what will that do? This 5th electron which is free will now start moving. When it starts moving, what happens? If there is movement of electrons, you say conduction is taking place. Conduction is nothing but movement of electrons, or conductivity is related to movement of electrons. The free electron now starts moving. And such a semiconductor, now this semiconductor is called as extrinsic semiconductor. It is no more intrinsic, it is called extrinsic, extrinsic, extrinsic semiconductors, and where the charge carrier is electron. Now electron is conducting, isn't it? Conduction is due to electrons. Electrons conduct, or conduction is due to electrons. Such a semiconductor is called as N-type semiconductor. N-type semiconductor. Now what is it? If I have to ask you to explain about N-type semiconductor, you can say silicon and germanium belongs to group 14, and the valency of silicon and germanium is 4. Now this intrinsic semiconductor is doped with electron-rich impurities of group 15 elements. Group 15 elements like phosphorus or arsenic. Phosphorus or arsenic occupies a place of silicon, and phosphorus has 5 valence electron, where the 4 electrons will bond with neighboring silicon atoms, and the 1 electron which is left free, or the free electron, will start conducting, and here the conduction is due to electrons. Now what has happened? It has increased the conductivity. That is what we wanted, isn't it? Why doping is done? Doping is done to increase the conductivity of semiconductors. We have done that now. Conduction is due to electrons, and such a semiconductor is called as N-type semiconductor. Hope you You got it? Now we will study what is a p-type semiconductor. Then it becomes easy for you to differentiate between these two. Now we will see what is a p-type semiconductor. In p-type semiconductor, now again you know silicon or germanium belongs to group 14 and the valency is 4 again. Valency is 4. Now this p-type semiconductor, you know, it is formed by electron deficient impurities. Which type of impurities? Here it was electron rich impurities, but here it is electron deficient. Deficient means less. Electron deficient, or they also call deficient impurities. Now since the name itself tells electron deficient impurities, one group less will be taken. So here group 15 was taken because we wanted electron rich impurity. Now electron deficient impurity, so group 13 elements will be taken. Group 13 elements will be considered. So example for group 13 elements can be boron, aluminium or gallium. Usually these will be taken as the impurities, that is electron deficient. Now let us consider what will be the valency here. Now the valency of group 13 elements will be 3. See, one less than silicon or germanium. Now in this solid, again, say if these are all silicon, all silicon here, or you can take example of germanium also, because however explanation is same, since silicon and germanium has all 4 valence electrons. So how many valence electrons silicon has? Silicon has 4 valence electrons. So it is like this: 1, 2, 3, 4. 1, 2, 3, 4. It will go on forming bonds with the neighboring ones, okay, by sharing of electrons like this. 1, 2, 3, 4. 4. 3, 4. 1, 2, 3, 4. 3, 4. This is how the bonds will be formed. Now what happens when you add an impurity, that is electron deficient impurity, say one silicon, any silicon, one silicon is replaced by one boron atom. If boron is the impurity that you are adding, boron occupies the position. Now tell me, how many atoms or how many bonds can boron form? Boron valency is 3. That means it has 3 valence electrons. Now those 3 valence electrons, what happens? You know, one electron will bond with one silicon here. One more electron will bond with one more silicon. One more electron, last third electron, will bond with one silicon. Whereas there is a hole created here, a vacancy is created here. See, this silicon does not have any electron here, isn't it? So that space is called as holes now. What is it called? Holes. H-O-L-E. A hole is created. Now what happens? There is a vacancy, there is empty space, hole. Now this hole, you know, some neighboring electron can come and fill into this. So what happens? From here, if the electron comes and fills here, then here the hole will be created. Now again neighboring atom will come to this place. Again one hole will be created. Like that, it looks like, when you just observe, you know, you see that hole is moving. But actually hole is not moving. One electron from neighboring comes and fills that. So this space becomes hole. Now for this, again one more electron comes and fills. The neighboring space becomes a hole now. So it looks like the hole is moving, and therefore we say holes are the charge carriers. Which are the charge carriers? Holes are charge carriers, or holes result in the conduction, we say. Holes are the charge carriers. C-A-R-R-I-E-R-S. Now hope you have understood such type of semiconductors are called as p-type semiconductors. Now it becomes very easy to differentiate. What is the difference between n? What is the difference between n-type and p-type semiconductor? Now easily you can differentiate that n-type semiconductors, the electron rich impurities are added. Here electron deficient impurities are added. 1 point. Then you can tell electron rich impurities like group 15 elements are added. Here electron deficient impurities like group 13 elements are added. That also you can tell. And here you can tell that the charge carriers are electrons. Here the charge carriers are holes. One more point you can again mention there, that here what is the valency of the impurity that you are adding? 5. So we call such impurities as pentavalent impurity. So you can say pentavalent impurities are added. Here the valency is 3. So we call them as trivalent impurities. Trivalent impurities are added also, you can mention. Hope it is clear. Maximum for 3 marks the question will be asked. So 3 points you must be remembering about n-type and p-type semiconductor. You need to understand the theory behind this also.